Okay, good morning, everyone, and welcome to this session today, which also concludes the week and the two-week workshop on the formal aspects of quantum gravity. And we have the last two speakers in this section, and we start with Leonardo Modesto from the University of Cagliari, who will tell us about non-local quantum gravity.
Okay, thank you very much. And I would like to thank the organizers for inviting me here. Actually, emotionally, it's very nice to be here for the second time to present more or less this topic. And the first time was many years ago. And in the audience, I still remember Professor Ifimov that appreciated a lot my new stuff at the time. So I will speak mainly about non-local quantum gravity, but in between, I will export many results. I will show many results also about local theory. So I will alternate somehow between non-local and local theories, and mainly I will focus on the unitarity and renormalizability, which I think are the main issues, just to define the theory, if you want to define properly a theory. So, as I said, I will review a quite large class, exhaustive class of local theories and non-local theories. Mainly, I will focus on unitarity, so no ghosts at all in the case of non-local theories, or complex pairs or fakions in the case of local theories that, however, are harmless. In other words, the theories turns out to be unitary, even if higher derivative. About supernormalizability is actually, that's the reason of my first comment. The properties are very, very similar, at least for the divergent part of the quantum effective action. We can go beyond, actually. It's quite easy. We can go beyond renormalizability, and that's quite easy. Actually, this was our main contribution by me and Lesa several years ago about finiteness. So we can go beyond that. We can really find quantum field theories that are finite. Local or local higher derivative theories that are finite at quantum level, no divergences at all. It's easy in odd dimension, but we can do the same in even dimension. I will mention some properties like something is quite new result, still under investigation, which is the resummation and then the corrections to the scattering amplitudes at the quantum level, not only at classical level, that we know from long ago what is actually the outcome. More recently, I also define this framework for the whole content of for the whole interactions and the whole content of matter in the universe. And mainly, we can have a non-local, or if you wish, local higher derivative theory, and even finite at quantum level, without need anything else than not quantum field theory. So they asked me to really start somehow from the beginning. Let me recap a little bit what we mean by a renormalizable or not renormalizable theory. Here on the left, for sure you know, but let me recap shortly. Even this little trick that you can, I can introduce. There is a pointer somehow. This. This. Which one? This. Oh.
Maybe so. Okay, so.
Okay, thank you. So if you consider quantum electrodynamics and then you focus, what is the problem? At tree level, of course, there is no problem. But when you compute loop amplitudes, usually you meet divergences. You meet integrals. These integrals are divergent, and you have to figure out something. And what Feynman invented is the renormalizability. Or in other words, if the contour terms, let me tell you a little bit more. Suppose you have this kind of a one loop amplitude, which is a correction to the photon propagator. This is you have two external photons in this amplitude, and you have a one loop integral in d4k, and two propagators, one for each one for one fermion in this case. So the divergence in a cutoff scheme is quadratic, fine, but we know, and this is the little trick that I usually teach to my students, we know that in dimensional regularization there are no cutoff divergences. Then, therefore, but only logarithmic divergences, which in other words means 1 over epsilon, where epsilon is dimensionless parameter. Then by dimensional analysis, you can infer that actually lambda square has to be replaced with b square, or actually box operator. Therefore, the divergence is proportional to exactly, if you of course also impose gauge invariance or preserve gauge invariance, f square. So how it works then? Usually you have you can always regularize any theory. You add to your classical theory the counter term, which is minus the divergent term, and the same perturbative order afterwards you can compute again the same amplitude, which will be finite. Because the counter term cancels exactly the divergent contribution. Plus, of course, the quantum correction, the finite quantum corrections that are really the news of the theory. Now you can see, again, this kind of operator is similar, in this particular case of QED, is proportional to what is already present in your classical action, the Maxwell action, actually. So, at least for this kind of a loop diagram, you can absorb this divergence in a redefinition of the coupling constant. In this case, will be eventually the fine structure coupling constant. In QD, this happens for all one loop diagrams and for any loop at any loop order. It's always the same story. All the operators you can generate to cancel all the divergences that you get are always proportional to operators present in the theory. These operators are just 2 or 3, depends on if there is mass or not. Therefore, this theory turns out to be renormalized. For all the divergences, you can always reabsorb in the same operators that you have at classical level. Fine. What is a theory in which this approach, this proposal doesn't work? For example, in the 4 fermion theory, in 4 dimensions. In this case, if you look at this diagram, 4 fermion interaction, you have again the same 2 propagators coming from the 2 fermions. You integrate in 4K. Again, you have lambda to the 4th in cutoff scheme divergence. Okay, I mean, there are people here from a syntactic safety or functional reduction group. So let me tell you that for me, and later I will mention again, beta functions are only the divergent part of the quantum effective action. Only the divergent part, okay? Because just to fix the convention. Then again, this quantity here in dimensional regularization by dimensional reasons can only contain p square, or actually the box operator. It means that the counter term you have to add to your action has 2 derivatives in the interaction. I mean, this is just a toy model. There are maybe other operators. I mean, this is just one candidate operator. You can eventually act with derivatives on different fermions and so on and so far. However, already this kind of operator is not present in your original theory. Okay, there is psi to the 4th, but there is no psi to the 4th with two derivatives. So you cannot redefine G Fermi in this case in order to cancel this divergence if you recompute the amplitude at the same perturbative order. So it's not contained in the original Lagrangian, such operator. At 2 loops, you can get, for example, this lambda to the 5th divergent eventually. I'm not sure, but let's assume. Can be 0 also, but usually it's not. And can be indeed non-zero because you can construct in dimensional regularization such operator with the right dimensions if you put this slash box square. Okay, and even this operator has 5 derivatives now. No, you see. and is not contained, of course, in the original Lagrange. And you can generate eventually all possible terms as far as you know for Fermi theory. That's the main difference between a renormalizable theory and non-renormalizable theory. Look at these three boxes or two boxes. These are exactly what you have in the original action. These are not. Always we are interested in the divergent contribution. Of course, if there are no divergences, you don't have any divergence, you don't have to normalize anything. Okay, so what about gravity? For gravity, it's exactly like for Fermi theory. It's not so mysterious. Gravity, you can expand in gravitons. The only difference is that usually when you expand, I mean, always, sorry, when you expand the Ricci tensor or the Einstein-Hilbert action in powers of the graviton field H, you get not only 3 graviton or 4 graviton interactions. This is a short notation that I hope everybody can understand. This is the kinetic term, 2 derivatives. And then you have a 3 graviton interaction, 4 gravitons, and so on so far. The difference is that you have an infinite number of interactions when you expand in H. But that's not an issue because what does matter is what is covariant. And these operators are at any order in the number of derivatives finite. Okay. So you can, in analogy with Fermi theory, redefine your field H in order to make it dimensionful. So now if you rescale with the Planck mass, H, you get now H dimensions full, and Planck square disappears from in front of the Lagrange, and it appears at the denominator of each interaction with the proper scale, a proper power of M Planck. Okay, let's play the same game for the one loop diagram, like for QED. We have 3 graviton vertex, and for each graviton now the propagator is 1 over k square. So unfortunately, that's the main difference between gauge theory or scalar theories or Fermi or standard model particle physics and gravity. The main difference is that you have 2 derivatives also in the vertices. Okay, this makes the difference. And in particular, you can have, if you put all derivatives if you act with derivatives on the internal lines on the propagators, you can have lambda to the 4. Lambda here is the cutoff. Lambda to the 4 divergence in cutoff scheme. Okay. And or less. You can eventually you can have even lambda square, not in Einstein-Hilbert, but if you act, for example, cosmological cost. Anyway, it's sufficient to focus on one and you spoil the normalizability of the theory. So lambda to the 4th in dimensional regularization means, again, 1 over epsilon. You have to match the dimensions, then you have to introduce box square. Now, by diffeomorphism invariance, this operator can only be R square or R mu nu square, or box R eventually, if you introduce also boundary terms. So, what's the outcome? This operator that you have to add to your original Lagrange, which was linear in R, is now quadratic in R, and you cannot absorb in a redefinition of your Newton constant, roughly speaking. So fine, there is no problem about, so it's not a problem of quantum mechanics. Quantum mechanics is a paradigm. Quantum mechanics is always true. Then you have to pay attention to the regime in which eventually you have some issues because of the theory, or maybe you can be not happy because the theory is not renormalizable, but you can always regularize the theory. And everything will be okay, like for Fermi theory, till the Planck mass. In this case, like for Fermi theory, till the W boson mass. Okay. Okay. Now, what happens even in, because actually, I don't want to make the story too long, but actually this divergence you can deal with, at least for pure gravity. But Gorov and Sagnot show that actually for gravity you have also R cubed divergence that you cannot eliminate with the field redefinition, but I don't want to go too in detail with this. So at 2 loops, indeed, you can have a divergence which is lambda to the 6, or actually box cube, and by dimensional reasons, this operator is Riemann cube. If it's Ricci cube, it's not a problem, but with this I can tell you later eventually. But Riemann cube is there, so there is no chance the theory to be renormalizable. This operator, again, it means that you cannot absorb this operator in a redefinition of your original Lagrange. Okay, now let me go beyond Einstein-Hilbert theory and classify a certain number of theories with different properties. Okay, this is the one we already discussed. It's non-renormalizable because the reason I told you. Again, we have a divergence at two loops, and then if you increase the number of loops, you have to introduce even a Riemann to the 6, Riemann to the 7, and so on so far, to infinite number of divergences. Increasing the number of loops, you increase the dimension of the operator that you have to add to your theory as a counter term. Okay, so another interesting theory, just to make quite, I don't want to say the most general, I always say this is the most general classification, but these are quite large number of theories, interesting theories. The Starobinsky theory, for example, goes beyond the Einstein-Hilbert theory, introduces also this R-squared term, which is only Ricci, not Ricci scalar, the scalar, I don't know, yeah, not R mu square, is R-squared. This theory has one more degree of freedom and is Gauss-free, but is from the quantum field theory point of view, from the renormalizability point of view, is even worse than Einstein-Hilbert theory. So here there are more divergences, is more divergent, loop diagrams are more divergent than not the Einstein-Hilbert theory. Already at one loop, you can have Riemann cube, okay? Because the propagator is has two contributions. One is 1 over p squared, the other is 1 over p to the fourth, and the vertex is also one vertex could be p squared and another p to the fourth, but if you cross these terms, you can have more than power 0 in the integration to one loop. So let's go beyond, and now we can deal with this very old proposal, I would say, which is quadratic gravity, in which you also have R mu square operator, Ricci square operator. And this takes exactly care not only of this extra problem that I just mentioned here, because the propagator now is 1 over p to the fourth, actually, for both the spin 0 and the sp2 contributions of the graviton to the graviton propagator. So it does care about this issue, but it does more because this theory turns out to be really renormalizable. This theory at any loop order cannot produce any other operator than not what is already present in this Lagrange. So it's very nice. Actually, in the beginning, it was claimed by somebody even here in the audience to be, and I think it's true, to be asymptotically free. However, for many years, people didn't take too seriously this theory because they were saying, and people still is saying, somebody is not yet happy, to be, I know. Maybe we can expand more in the discussion. We have to figure out how to fix this issue of the instability, the ghost instability. And to me, the best way, and the one at least I understand better, and later I will tell you something depending on time, I think, well, I can tell you something, is the Anselmi-Piva prescription. Right? You have to introduce the proper prescription in order to take care of this. And unitarity you can prove. Then you can tell me, I don't like, fine, maybe it's fine. But it's for sure correct the optical theorem. For sure the optical theory is satisfied. Okay, let's go beyond, otherwise. I can change even this. Okay. So then, to me, indeed, actually, like more finite theories or super normalizable theories, and maybe if I will time later or in the discussion section, I can tell you why. So you can go beyond. You can take this more higher derivative theory proposed actually in the beginning by Asorey, Lopez, and Shapiro. And this theory, in principle, can have even more ghosts, but you can still apply, since they are massive, there are no issues in applying the Anselmi proposal, Anselmi-Piva prescription, and is unitary. Not only unitary and super normalizable, but even finite if you take n, for example, equal 6 derivatives, at least 6 derivatives super normalizable, finite, I think 8 or 10. So you see, you don't need any artificial, I would say, more recent proposal to achieve finiteness. Standard quantum field theory, exactly like standard model particle physics, can achieve finiteness and unitarity at the same time. Maybe failing something, but in these two, no. Anyway, let me also mention this theory, which is actually not normalizable, but at least unitary, because there is no box operator. You can always eliminate all these box operators at non-perturbative level in order to make the propagator 1 over p squared, so there are no ghosts and the theory is unitary. But these theories are not, for sure, not normalizable. Are different kind of theory that I like to mention here. Okay, what about non-local theories now? Well, the non-local theory, you can, the simplest one is when you replace the box operators with an entire function, actually. Don't pay attention to this 1 over box, because this is an exponential, so the ratio is an analytic function, okay? So what is the main property? So there are properties that are very similar to local theories, and now I tell you why. Because there is a very interesting class of functions that are consistent with the power counting theorems, and these functions are asymptotically, polynomial. So if you take large zeta, this box operator in flat space time, you can think like k squared. And when you have to compute a loop diagram, what does matter actually is the large box or large k limit in the loops. So this function e to the h dominates on anything else for large zeta or large box, and asymptotically, again, for large zeta is a polynomial, p of zeta. P of zeta is p of k squared, is a polynomial. And you can even expand asymptotically. You see, is a polynomial, this guy, plus something which falls off. So these extra corrections matter for the quantum effective action, of course, but not for the divergences. So it is like asymptotically polynomial theory. In the sense that many results that we found or we can find in local theories coincide with the same in the non-local case. In particular, the power counting analysis and the divergences are the same. So keep in mind that I mean, this is a crucial. So it's a large class, in principle, an infinite class of theories. Okay, but with this asymptotic property. So in the infrared, you have Einstein-Hilbert. This guy is just r squared plus r box r, etc. In the UV is a polynomial theory like g box to some power r. Okay. Is it clear to the students mainly? Okay. Now, unitarity of non-local theories. Since of non-locality, the propagator of the non-local theory only turns out to depend on this function e to the h. I mean, here I'm expanding around Minkowski because only there is well defined the unitarity issue. Of course, stability is well defined on any background, and that's another story. But for the Minkowski space-time, stability and unitarity are the same. And it turns out that the propagator up to gauge-dependent terms is an exponential divided k squared. Actually, this is exactly the same of Einstein-Hilbert for capital H equals 0. Well, something I forgot to tell you is that h of 0 is 0, so this exponential is 1. That's the property of the entire function. So already, if you are familiar with the unitarity issue, can claim unitarity, because what you have to do to be more precise at classical level, you have to compute the amplitude with two external sources, currents, or actually for gravity, the energy momentum tensor, the propagator. Here, all the eyes should be in the proper with the proper power. And in this slide, I'm using the signature minus plus for the Minkowski metric. This is again the gauge invariant part of the propagator. Notice that here I was even more general. There are two form factors. In the previous slide, it was only h, no, e to the minus h. But actually, you can have two different form factors. Okay, you can look at the references eventually. Just to show that if these two form factors are different, but h2 of 0 and h0 of 0, evaluated both in 0, are 0, then the unitarity is satisfied. In particular, what you have to do, when you replace the definition of the S matrix in terms of the amplitude, t, tau, or m, the condition S dagger S equal 1, which is unitary. I think everybody agrees on this. This is the really basic bridge. The implication is that the imaginary part has to be positive. Okay, so you can compute this amplitude. It's very simple. T mu nu is conserved because the theory is diffeomorphism invariant. Therefore, that's the reason why I don't pay attention to these extra gauge dependent terms, because are all zero since of gauge invariance or diffeomorphism invariance. The same for gauge theory. You can do the same for gauge theory, Jan Mills. Anyway, so when you do explicitly the computation, even if H2 is not the same of H0, the replacement of when you rationalize here the denominator, you get the Dirac delta definition for epsilon to 0 with the Feynman prescription, and delta for on shell makes the graviton on shell, and in particular these two contributions are simply 1. So you get exactly the same result that in Einstein-Hilbert theory. You have just to check, but it's the same that in Einstein theory this quantity is positive. So the real, the imaginary part is positive, or the residue is positive. So this is the 3-level proof. Okay, it's not enough for in quantum field theory, but this is known from long ago, from Krasnikov and Kuzmin mainly. Okay, what we can do at quantum level, what we have to do at quantum level. At quantum level, your theory you can define in Lorentzian signature, fine, so your path integral, okay? But every time you meet a loop diagram, in the loop diagram, the internal energy is Euclidean. In the beginning, you can take also the external energy to be Euclidean, and then you make the analytic continuation, okay? This works, of course, even for local theories. I mean, for standard model, you can prove in the same way. But the Euclidean and the Minkowskian theory, so the one in which you integrate along the real axis and the one in which you integrate along the imaginary axis, are not equivalent for are not the same, or actually in the non-local case, you cannot even define in the non-local case, indeed. So the path in which you have to integrate is this one, but you can do explicitly in a simple case. For example, this was done with Fabio Briscese in the beginning, so you can take the bubble, or in the 5 to the 4th theory, the scattering amplitude. You have two propagators. This is a simple non-local theory, scalar field theory, non-local theory, and even finite, just to make things simpler. You have 6 poles in, sorry, 4 poles in your energy plane K0. Okay, and what you have to do is to compute the imaginary part of the amplitude, like at 3 level. And the imaginary part is is actually the discontinuity of the amplitude for epsilon to 0. For the discontinuity is defined like m minus m star, no, the imaginary. Now, it turns out that the result is the same of the local theory. As long as these form factors are 1 on shell. And indeed, on shell, you see there are 2 delta that actually makes these 2 form factors equal 1. If not, you have a constant contribution, and then you have to define your optical theorem in order to take care of that. So it works anyway. So as I said, you can in the beginning integrate your loop. You can make your loop integral along the imaginary axis, and you deform your imaginary path to a new path when the external energy E P0 becomes real. Here P0 external energy is complex. And then you make real. Okay. So when you make it real, one of the poles, exactly K4, pinches the imaginary axis and goes in the second, this region. Second square. First, this one. What's the name? I mean, this part. And it appears now to be right there, over there. So the analytic continuation means you have now to integrate in this funny path, which is a simple case of the previous slide. But this integral is not difficult to make because it's just using the Cauchy theorem, the contribution along the imaginary axis plus the residue. Okay. So the contribution along the imaginary axis does not have any imaginary part in the discontinuity, does not provide any imaginary part to the discontinuity. The only contribution comes from the pole. And in the end, you get this formula. First, you have to compute this, and then you have another 1 over I epsilon, which produces actually the other delta distribution. Okay, so this is a toy model. You cannot trust eventually this computation because it's too mathematical. So you can say, well, let me compute this explicitly. Let's really do it. Let's take this particular four factor. You have the amplitude, as I said, the integral you have to make is along the imaginary axis plus the residue. So there are two contributions. And this is the result of the previous analysis. But you can do explicitly. You can even compute, and I will show you in 2 slides, the final result of this amplitude. So let's focus on MI, which is the integral along the imaginary axis. What you get when you define K0 to be I K4 is an integral in R4, actually. And this is the simple thing you can verify later, eventually. We would like to see the discontinuity, if there is. And the real part is not, in general, is non-zero, but the imaginary part is 0, because if you look at this integral, there are two contributions, and both are an odd function, and both are odd functions integrating from minus infinity to plus infinity. So this is an odd function in K4, because the sign, and this is cosine times K4 for epsilon to 0, this is 0. So the imaginary part does not give, the integral along the imaginary axis does not give contribution to the imaginary part. On the other hand, the residue gives this very well-known result for local theories. So it's exactly the same you get in local theories. Okay. So this is, well, maybe there are other ways to write. Yeah, no, I know. Yeah, you can. Well, for the non-local case, you can't get the same result. You can't get the same gamma function. With the exponentials too. I don't know. We can discuss later eventually. Okay. But by the way, here we didn't go to the end. We just show if the imaginary part is 0 or not. But, I mean, if you have something more powerful, I will be happy to. So numerically, we computed, however, and actually my student did, and you can see that the imaginary part is the usual one. There is the usual threshold at the mass m in the theory. Actually, is 2m. Here m was 1/2, I don't remember. And the real part for small energy, for small p0, is very similar, overlaps to almost with the local case. But for large energies, it's not just logarithmic, the behavior, but it's more exponential behavior. This I don't want to discuss now, but it's a very important result to me. We can do the same for box to the fourth, and this is the plot for the three cases: the local case, box to the fourth, and box square. Sorry, not box to the fourth, k to the fourth, and box square. Okay, fine. This is about unitarity, another technicality that I can skip. What about gravity? About gravity, this actually was derived by a student of this diagrams was derived by a student of Anselmi several years ago, and I just modified a little. Anyway, what is the difference between a scalar theory and a gauge theory or a gravitational theory? Yeah, you have to pay attention of the gauge invariance, therefore BRST invariance, and finally the word identities. So it's very more involved, but what does matter is the behavior of so we know now the Katkowski rules, and we know that when you cut a diagram, the discontinuities are all proportional to the distribution delta of k squared. And all these cut diagrams that appear in this diagrammatic formula are proportional to delta of k squared. Okay, so whatever is your numerator, as long as it's an analytic function, an exponential, will not affect this proof. Okay, because when you cut, delta of k squared will make your exponential 1. So this result, and now I'll tell you what that actually means, applies also to local or non-local theories as long as the delta makes any extra term equal 1. So what this means? It means that because of gauge invariance and BRST invariance, the propagator that we know contains also the longitudinal, not only transverse, but also longitudinal and 0 modes, when, in order to satisfy the optical theorem in which the gluons, the gauge bosons, can go on shell when you cut the diagram, you have to cancel such contribution with something, and that something is already there are the BRST ghosts that makes properly their job. So they cancel the longitudinal and 0 modes, and finally you get the propagator which is transverse, okay, without any extra degrees of freedom propagating. So everything is consistent. This applies, the main thing is this factor here, which appears for all these cuts, even for non-local theories. Okay, all these results you have to derive expanding around Minkowski space-time, and so the original theory is, of course, gauge invariant or diffeomorphism invariant. Fine. Then you expand around Minkowski, and there you can define all these things in which k mu is really the ordinary derivative. Okay, k mu here is the ordinary derivative. Oh. No, you can't because of the word identities. Yeah, you can't. Perturbatively, you can't. I mean, gauge invariance is guaranteed by BRST invariance at quantum level. So everything you have to do everything properly, of course. I mean, this should be which reference I can tell you. Bookbinder again, chapter 2. There is an analysis for any theory. Any theory you can provide. I think nothing to do with something exotic. It's really pure gauge invariance and BRST invariance. So that's it. Okay. Okay, so I would like to tell you something about then again the unitarity for the local theories. And in particular, first, let me tell you that it's extremely important to provide a mechanism to read out of the ghosts. It's not sufficient to say that the ghosts have a very a very large mass. Okay, because even if the mass is 120 times the Planck mass doesn't work. The ghost has no there, or you have to provide some prescription for him in the theory, or has to have the mass which is exactly infinity. Oh, so how you can see this? Well, there are many references. I like the one by Maggiore. I don't know. So suppose you have a theory with with the normal particle and the ghost. If you have a ghost and you only assume energy conservation, which is a consequence of the space-time translation invariance, and you have also an interaction between them. So the vacuum the key in, for example, in this theory, two ghosts and two normal particles in zero time, not small amount of time, exactly zero. So it means that the vacuum in this theory, or actually the classical solution phi equal psi equal zero, does not exist. Okay, so you cannot, in the case of gravity, or let's say gravity, it means that Minkowski spacetime does not exist. So, of course, the empirical evidence is not that way. Again, if the mass is very large, doesn't matter. I mean, the energy is conserved, and even if the ghost is at the mass Planck, the Minkowski spacetime now cannot exist at our energy scale. Okay. So you have to provide some mechanism. So in the beginning, chatting and discussing with Shapiro, we thought to solve this problem in gravity, considering not non-local theories, but local theories with complex conjugate pairs. Why? Because if you look at the formula that I presented in the beginning, one way to make the imaginary part positive is to have an exponential of some entire function, or to have some operator in between these two Einstein and Ricci tensor, such that when you take the imaginary part, you don't get any contribution. So the polynomial has to be such that it has only this kind of polynomial, only complex conjugate poles. Because when you take the imaginary part, of course, you don't get any contribution from them. And again, you have imaginary part of M positive. So this formula actually is for this theory, but you can have more higher derivative theories, but as long as you have complex conjugate poles, it works the same way. This was 3-level. Our computation in the appendix at one loop was wrong, actually, but 3-level was correct, and the theory was a nice proposal. Later, Anselmi and Piva expanded a lot on this, especially, let me skip something, because especially for the case of real particles, and they introduced the concept, real ghosts, and they introduced the concept of fakions. So, in other words, the proposal, when you go to study the theory at perturbative, the unitarity at perturbative level, is the following. At the classical level, you assume these particles to not be in the Hilbert space, the asymptotic space of the asymptotic space. Okay, is not there. You remove, and for let's say quadratic gravity, it means that you have only the graviton, eventually the Starobinsky scalar, but you move out the ghost. Now, the idea is that these ghosts cannot contribute. You have to find the right prescription in order to preserve this property also in at loop level. And then the Feynman prescription doesn't work. What you have to do is a little bit more. And the recipe is the following. You take your loop diagram. You make first the integral in the energy. You apply the usual formula to these fractions, which is the principal value plus the delta distribution. and you trash away all the deltas that contain ghosts, the ghost particle. The outcome is that you finally end up with this integral, and the amplitude now contains the log of the absolute value of p squared. Okay, this is this is one of the three ways to implement this prescription. Is the simpler one to present. There are also other two a little bit more involved, but the outcome is this one. So it's a matter of logic here. You can like, you don't eventually, but you remove your ghosts. As long as you are able to do not create again in loop diagram such particles, then the proposal is consistent. Okay? And this is the logic, as far as I understand. And in short, you could say that if you take the Feynman amplitude, which is log of p squared, massless here, the simplest case, with the AP prescription, actually, you have to take this arithmetic average, which gives you log of absolute value of p squared. And of course, this one has imaginary part. In the signature here has to be minus plus. And this one has not, because of the absolute value. It's p squared squared. Okay, so no imaginary part. It means that if you have a theory like, I don't know, this is even too complicated. Let me go back. If you have a theory like this, you have the normal, only the contribution of the particle with mass little m square will contribute to the imaginary part of the theory, but this one, which is actually the one with complex conjugate poles, a little bit more involved, does not. Okay, so you remove the complex conjugates pose from the spectrum, and you cannot generate according to this prescription at any loop order. So unitarity, or actually the optical theorem in the subspace of physical states, is preserved. That's the statement which has been proved. Okay, maybe later we can discuss if there are objections. Okay. What is the difference in the quantum effective action? Well, in the non-local case, if you have one normal particle, you get the usual peak at the threshold. This is the real part. In a local case with higher derivative, you can have also these extra peaks due to the pairs, these complex conjugate pairs in this case, that are that give contribution to the real part, but not to the imaginary part. So in principle, in an experiment, you can see the difference. Okay. Well, I didn't say anything about renormalizability. Okay, 10 minus, I guess, right? Okay, let me come back to non-local theories, but actually this is true for local theories as well. Why? Because the non-local theory, as I said, has this asymptotically polynomial eigenderivative theory, the eigenderivative limit, and plus corrections that follows that do not give contribution to the divergences. Shortly. Yeah, here, yes, for sure. Here for sure, yeah. But when you make when you have, if you're going Minkowski space-time, and you have to expand everything around Minkowski. And there are nice formulas to expand even these functions. Of course, I don't want to use bad words, but I mean, it's not that easy to make, but we can do. Somebody like Lesla, for example, did several times. So you have to vary G, you have to vary R, but you have to vary also the exponential, you have to resum, and there is this nice formula actually from the original paper by Kuzmin that we discovered later, but there is this formula, or at least there is a way to compute. Say again, what I this one you I mean, as I said, I do not forget diffeomorphism invariance. I mean, everything is covariant. because so everything is taken into account. I do not cancel by hand or forget anything by hand here in this in the computation in principle. In principle. But that issue eventually is already in this polynomial operator, if you wish. Since, as I said, this does not contributions to divergences, and I wanna make a power counting analysis of the theory, let me focus on the local Eiger derivative limit. So, if you wish, and you like more local theories, you can even forget this operator and just say, oh, okay, my theory is the one with the red operator. P is a polynomial. Okay, of the covariant box operator. So how you make your power counting analysis, I mean, roughly. Asymptotically, as I said, in short, here I wrote R, which can be Ricci or Einstein or scalar R, whatever, any covariant, any contraction of the Riemann operator, and a box of some power, integer power. This will be an integer power. This was a notation that we introduced in the beginning. So you have R. So the leading term for the propagator and the divergences, if you want to make an analysis of the divergences, is just this one. Is exactly a generalization of Einstein box to some power coming from this and Ricci. Okay, fine. So what is the main difference, as I said in the beginning, between gravity and a scalar theory or more simple theories, is that the propagator now scales like 1 over pi to 2 gamma, some integer that could be, for example, 3, plus the dimension of the space-time in this notation, so some power of n, and if you take n large enough, you can make the propagator to fall off very fast. But unfortunately, even the vertex, in the worst case, scales in the same way. So in the end, however, it turns out that thanks to this propagator, only if gamma is big enough, and I said in dual 4, gamma has to be bigger than 2, it turns out that there are no divergences at any loop beside L equal 1, because as you can see, gamma cannot do anything for divergences at one loop, because for L equal 1, you have D. So it means that the theory is super normalizable because you have divergences only at one loop if gamma is big enough. And the divergences in 4 dimensions are the same of quadratic gravity, at most. So R, cosmological constant, R square, R mu square, boundary term, okay? This for divergence. Riemann you can always express in terms of Ricci square and R square. So normalizability means that you have divergences in this case only at one loop or up to some loop order, but not at any loop order. And for gamma equal or bigger than 3, you have in gravity divergences only at one loop in D equal 4. Here are the counter terms. However, the theory is super normalizable because quadratic terms are already there, so you can renormalize the theory. There is not too much time. I want to tell you now something about beyond renormalizability. So the outcome of this seminar mainly is that we can achieve unitarity and renormalizability in both Eiger derivatives and non-local theories with different features and similar features too in some limit, and that's it. Now, can we go beyond renormalizability? So there is a very simple way to go beyond renormalizability in 5 dimensions, because dimensional regularization, in all dimensions at one loop, there are no divergences. So all the divergences at one loop have this structure. And if you look at the pole structure of the gamma function, you see that since n and k in our theories are integer, while d over 2 is semi-integer, then this gamma has no poles. So no divergences, for example, in d equal 5, if you wish. So this theory is finite in d equal 5. Say again? But 2 are not there because of the power counting analysis. Of course. Now, what about 4 dimensions? Well, in 4 dimensions, we cannot use this trick or this result by dimensional regularization. By the way, it's not that in another regularization scheme there are divergences. You can do the same analysis in power count in a cutoff scheme, but in a proper way with the Pauli-Villards, take the mass of the Pauli-Villards to infinity, etc. You get the same result. Okay, because this is important point. So any result which is scheme dependent, we don't trust. The regularization scheme dependent, we don't trust. So now, in 4 dimensions, what we can do, what we did actually. Well, we said we know the beta functions get contributions. Again, the beta functions are the coefficients of the divergent part of the quantum effective action. So our operators like beta is this number, and then the divergent part will be r mu nu square, r square, consistent with the power counting analysis. And 1 over epsilon is exactly the divergence, the log divergence. Okay, so this is what we find at one loop. We get contributions to these beta functions from the asymptotically polynomial limit that here we wrote in this form of this operator, okay? And we do not expect to be exact, it could be 0, because we don't have yet the final result for this computation. And we think at least the Ricci square contribution will not be 0, or Weyl square, one of the two. However, we can add to the theory a kind of potential. I call this potential because these two operators that we can add to the non-local theories are local, of course, but are quartic in the Riemann tensor. Ricci and R tensor, R scalar. So it means do not spoil, do not change the three-level unitarity and unitarity at all in Minkowski space-time. So the propagator is the same, but they give contributions to the vertices. Therefore, you have extra contributions coming from these two operators that originally we call killers, because they were able to cancel the divergences, to kill the divergences. And the beta functions will have this kind of structures depending on S1 and S2. So the nice property of these two operators is they contribute linearly in S1, S2, these two coefficients, okay? So you can always solve this system and get 0. Notice, this is not a fixed point, or at least the theory is at a fixed point in some terminology, in the sense that this is exact, it's a one loop exact. At 2 loops, you don't have contributions to the beta functions. At 3 loops, you don't have contributions to the beta functions. So this is the final result. Unfortunately, I cannot tell you exactly what these two numbers are because we don't know yet C1 and C2, but it's just a matter of sit down and compute the full contribution to the beta functions in pure gravity due to all the other vertices. And then you will have specified completely your theory with some fixed numbers. Okay, it's clear what I mean. With such theory, with fixed, this is a way to derive the two coefficients. But once you have, the theory is finite any loop order. Okay. So it's not fine tuning, and it's not. Okay. Well, since it's time to stop, I can stop here and I can tell you something else or expand on this later. Let me just go to last slide. Because there is something nice about cosmology, but this was more an introduction to the theory. So thank you for attending.
Leonardo. We have time for a couple of questions. Richard?
Changing quantum field theory, because what's the classical limit of the changed quantum field theory? It cannot be the original theory that you started out with, because the quantization of that theory leads to the one that you don't like. So it must be something else. What is it?
So actually, I'm not changing quantum field theory. I'm just changing the classical theory. And then I apply the path integral, the standard path integral approach to a new theory, which could...
Or that's not true. Suppose you take the Stelly theory, for example. the naive quantization of that has negative energies, right? Because the classical theory does.
Okay, you are speaking. So there are two theories here. Just a second. There are two theories here. One is non-local and one is local. The local one can needs a prescription. This is what you eventually mean by different quantization. You are right in this sense, but you always have to provide a prescription.
Local, the original classical theory looks like, because we don't have any low energy quantum gravitational data. The only thing we have.
Well, the low energy limit is always Einstein-Hilbert theory, even from the action, classically.
It cannot be that. Okay, so your answer is that it's Einstein-Hilbert, right? That's your answer.
The low energy limit has to be.
The low energy limit. Classical theory, the exact classical theory that corresponds to the changes you make in function. You claim that the exact classical limit of that is Einstein-Hilbert. Right?
So I have very under control the non-local case. In the local, in which there is the classical theory is what I wrote, and then you quantize and you have quantum corrections. In the case of the local theory, you have to integrate out properly. You have to solve the equations of motion for the ghost and plug in your classical action to get your original action to get what is your theory, your final theory. Okay, there is no classical theory in this sense. You can find the classical theory with this procedure of solving the equations of motion for.
I can answer that.
Okay, please.
It's about the local theory, right?
I'm talking about if you.
Yes, I think so.
All I want to know is if I were trying to look at the classical theory associated with that, what is it?
Yeah. So in the local case, it is Einstein plus additional non-local vertices that I can show you. That I talked about that in the last week talk.
Okay, I'm sorry, I was not here last week.
Yeah,
but that's
the exact classical energy, not just Einstein. In the low energy, it will be Einstein. There will be extra
Einstein plus things that would.
no local vertices that average away in everyday life.
So in other words, the statement is not still, it's not quadratic.
Classical energy is not the steady state.
Okay, thank you.
Okay, thank you for helping me in this.
Are there other questions, Luca?
You mentioned something about the resolution, but I guess there was time to.
Well, actually, not only matter of time today is that we are still work in progress. Okay.
What is the aim there?
Usually, the statement is that the amplitude should be very soft in the ultraviolet. Okay, that's the statement. Usually, when you resum, you get 1/1 plus log k squared. Okay, when you resum the bubbles, one loop, one pi contribution. Here, we expect to have 1/, it depends on the theory, even e to the e of k squared or s. So something extremely soft.
Resumming the propagator or something?
Well, at the moment, only the 1 pi for the propagator, yeah.
Because from there, it's difficult to see how an exponential can appear.
Oh, no, that's for the propagator is easy. You cannot be sure eventually, but should be the same because there are, I mean,
because the self energy is still exponential or something, right?
So the propagator, oh, yeah, but it goes to zero even more than the classical one. Yeah.
Okay.
Because the three-level amplitude, especially in gravity, is the same as Einstein-Hilbert, no? So the unitarity bound is still there. So what happens beyond the Planck scale eventually? So there something has to happen. Or you resum or you take another theory. And my proposal is to resum. Some toy model shows that actually the scattering amplitude seems to scale not like S, but S times e to the minus e to the S. So something that goes very fast to zero. But it's work in progress.
Yes, perhaps we can postpone this discussion to the open discussion session. So let's thank Leonardo again.